Good morning, my name is HENG, and today we will be presenting our case study, the Smart Mailbox Notifier. We live in a world of hyperconnectivity. You can track an order from a warehouse in China all the way to your local delivery hub. However, once that package leaves the delivery truck, we hit a blind spot. We call this the last 50 feet logistic gap. While the last mile problem is well known in logistics, the last 50 feet refers to the gap between the delivery vehicle and the homeowner's hand. This disconnection results in a loss of visibility, security risk, and inefficiency. Today, we are proud to present a solution that bridges this final gap, transforming the humble mailbox into an intelligent connected device. We have the first thief issue. The rise of e-commerce has led to a direct increase in package theft. Because residents are not notified immediately upon delivery, package sits vulnerability on post or in unlocked box. Second, the dumb mailbox. Traditional mailboxes are passive. They offer no connectivity. Residents are forced to manually check them, which is a waste of time and often results in missed deliveries or failed notification. The third, resource inefficiency. Without an intelligent mailbox framework, courier resources are often wasted on redelivery attempts because the homeowner wasn't aware the package had arrived. The fourth, lack of personalization. While we have centralized parcel lockers in public space, there is no widely adopted localized smart system for individual landed properties or homeowners. Our proposed solution is an energy-efficient, event-driven IoT architecture. We are not just adding a camera to a mailbox. We are rebuilding the interaction model. Our system transforms a standard mailbox into an intelligent mailbox capable of three things. The first, accurate detection. Using laser technology to physically verify the presence of a package. Second, extended autonomy. Using advanced microcontrollers and deep sleep modes to run on battery power for extended periods. The third, real-time user connection, delivering immediate notification to the homeowner's smartphone to enhance security and reliability. This ensures that the moment a parcel is dropped off and the homeowners know about it. Let's open up the hood and look at the high-level system architecture. We have organized our system into a robust 4-layer hierarchical model. Layer 1, the physical sensing layer. This is our ground truth. We employ two sensors here. A magnetic reed switch acts as our trigger. It detects if the door is open or closed. A VL 53L0X time of flight TOF sensor acts as our verification. It measures distance to confirm an object is actually inside. Layer 2. The logic layer data from the sensor is fed into an ESP32 microcontroller. This layer runs a differential state change algorithm. Its primary job is to filter false alarm, ensuring that a leaf blowing into the box doesn't trigger a package arrive alert. Layer 3. The communication layer. Once the logic layer confirms an event, the data moves here. We use an external UFL antenna over 2.5 GHz Wi-Fi to ensure the signal can penetrate the mailbox enclosure and reach the home network. Layer 4, the interaction layer. Finally, the data reaches the user. We use a Mosquito MQTT broker to handle the messaging, which then pushes an alert to the user via the Telegram bot API. This provides a seamless instant alert on homeowner's mobile device. Next, let's dive into the toolchain justification. First, the microcontroller ESP32. We select the ESP32 specifically for its ultra-low power URP core processor. In a battery-powered IoT device, idle current is the enemy. The ESP32 allows us to drop the idle current to just 12 microamp, which is essential for battery longevity. Second, the sensor, time of flight, TOF. A common question is, why not use a cheap ultrasonic sensor? Ultrasonic sensor use sound wave inside a small metal mailbox. Those sound waves bounce off the walls, causing multiple path interference and false reading. The VL53L0X uses laser light, which is immune to this echo effect, providing accurate detection in narrow enclosure. Third, the protocol, MQTT. We chose MQTT because it utilizes in a lightweight JSON payload. For an intelligent system that demands low latency and low power, MQTT is far superior to standard HTTP protocols, allowing us to send data quickly and put the device back to sleep. Then, let's dive into the bill of materials. A smart city solution must be scalable, and to be scalable, it must be affordable. We conduct a detailed bill of material analysis. Our core components include two ESP32 microcontrollers, approximately 64 ringgit. Solar power system. This includes a polycrystalline solar cell, cost almost 32 ringgit, and a MPPT solar charger, which costs almost 16 ringgit, to ensure the device is self-sustaining. Sensing. The VR53L0S sensor costs just 9 ringgit and 50 cents, and we have a magnetic resist cost just 3 ringgit and 50 cents. The 18650 Leon cell costs almost 10 ringgit, and 1 ringgit of 18650 battery holder. And last, a TP4056 module costs almost 2 ringgit. Here is how the system thinks. The workflow begins by reading the battery voltage. If the battery voltage is less than 3.5 volt, the battery status is set to low. If the battery voltage is higher and equal to 3.5 volt and lower than 4 volt, the battery status is set to medium, or else the battery status is set to high. At the same time, the workflow will also begin by reading the sensor. There are two cases where the sensor detects the presence of the object, or the sensor does not detect the presence of the object in the mailbox. If the sensor does not detect any object in the mailbox, the parcel status is set to activity detect. For the second case, if the sensor detects an object in the mailbox, the parcel status is set to parcel retrieve, or else the system will check if the door of the mailbox is open or closed. If a sensor does not detect an object and the door of the mailbox is closed, the parcel status is set to empty. If the sensor detects an object and the door of the mailbox is open, it will output a message stating the parcel retrieved, the parcel delivered. The system will then send the data of the door status, object status, parcel status, and the battery status with the timestamp to the user using a Telegram bot API. We utilize a hybrid approach. For internal data transmission and communication with external microcontrollers, we use MQTT. Its lightweight structure minimizes the radio on time, which is the biggest drain on the battery. Because sensor and microcontroller are often close to each other, the MQTT is highly efficient. However, to reach the user, we need Wi-Fi. While Wi-Fi consumes more power, it provides the extensive range and high data rate needed for real-time Telegram notification. To mitigate the high power cost of Wi-Fi, we heavily rely on deep sleep mode. This allows us to reduce energy usage by a massive 83.38%, making the system compatible with solar power operation. That's all from me. Thank you.